Let's look at OpenStax University Physics Chapter 10, Problem 94. Consider the circuit below. A. What is the initial current through resistor R2 when the switch is closed? B. What is the current through resistor R2 when the capacitor is fully charged long after the switch is closed? C. What happens if the switch is opened after it has been closed for some time? D. If the switch has been closed for a time period long enough for the capacitor to become fully charged, and then the switch is opened, how long before the current through resistor R1 reaches half of its initial value? So let's take a look at the circuit. We have a battery, we have a power supply that when we close the switch will send current through this circuit. Now, when the current is first starting to go through the circuit, it branches out, and we know that a capacitor will act as a wire. So when the current wants to branch out here, it realizes that this is the path of least resistance. This is basically a wire compared to a 10 kilo ohm resistor. So the current will always take the path of least resistance. It will bypass R1 and go through the capacitor, which is just a wire, and then it will go through resistor R2. So when we first close the switch, R1 is going to be short-circuited. It's going to be bypassed by this other wire in the circuit that will let the current go through much more easily. So when we close the switch for some time, it will get harder and harder for the current to go through the capacitor, and the current will split up between the capacitor and the resistor, and then a long time later, the capacitor will be fully charged. It will act as a broken wire, so the current will only go through resistor R1 and R2 in this little circuit. When we open the switch after the capacitor is fully charged or has some charge in it, the capacitor will push charges through the resistor in the opposite direction that it was going in before, and this will happen until the capacitor discharges fully. So this is what the problem is, and now we have to look at the knowns and unknowns and see what it is that we're looking for. So what we know are the power supply is 24 volts, R1 is 10 kilo ohms, R2 is 30 kilo ohms, capacitance 1 is 10 microfarad, and in part A, we're looking for the initial current through resistor R2 when the switch is closed. So when the switch is closed, we call that time is 0, and we're looking for current through resistor 2 at that point. Then we want the current through resistor 2 when the capacitor is fully charged, so that's going to be my time equals infinity, long time later. So we want, again, current through resistor 2. In part C, we want to know what happens if the switch is opened, S opened, and we have to discuss that basically. And in part D, if the switch has been closed for a long time, long enough for the capacitor to become fully charged, we want to know how long, so we're looking for the time it takes for the current to be the original current through the resistor divided by 2. All right, so let's start with part A. So again, in part A, it's t equals 0. So we're first closing the switch, and the current is going to start flowing through here. It will take the path of least resistance, so the circuit we have in part A is this. This is all there will be in the circuit for part A. So we want a current through resistor 2, and that's just V1 over R2. V1 is 24 volts, R2 is 30 kilo ohms, and we get 0.8 milliamps going through the resistor. Then in part B, we're looking for the current through the same resistor a long time after the switch was closed. So a long time after the switch is closed, the capacitor had a chance to fill up completely. So now the capacitor acts as a broken wire. So the circuit that we have now looks like this. So this is the power supply, this is R1, this is R2, and where the capacitor used to be, we just have a broken wire. So then when we solve for I2, by Ohm's law, it's going to be V1 divided by the equivalent resistance, and R1 and R2 are connected in series. So I have R1 plus R2 here. So V1 is still 24 volts divided by 30 plus 10, that's 40 times 10 to the third ohms, and we end up with 0.6 milliamps. Now in part C, we're supposed to discuss what happens after the capacitor is charged and we open the switch. So we know that the capacitor will charge with positive charges on the top plate and negative charges on the bottom plate, because this is positive, so that will be positive as well. So if we open the switch again, these positive charges are going to travel in this direction, and the capacitor will discharge through the resistor, through resistor R1. And that's all that happens because this is broken, so there is no current flowing through this branch over here. In part D, we want to know how long it takes for the current going through this resistor to fall to half its initial value when we first opened the switch and the capacitor started discharging through the resistor. So we know that V is V naught E negative T over tau. Is this the correct equation? So we want, when we first close the switch again, the capacitor to be charged. So there should be a voltage across the capacitor. So that means that when I plug in T equals 0 at the point when we are opening the switch again, then I have e to the 0, which is 1. 1 times V naught is V naught, so the potential across the capacitor is not 0. So this is the correct discharging equation. Now if I use Ohm's law, I know that IR is I naught R e to the negative T over tau. So I divide through by R, and now I'm going to divide both sides by I naught. So I have I over I naught is e negative T over tau. So let me make more space here. So now if I take log of both sides, log of I over I naught is equal to negative T over tau. And I'm looking for the time. Time will be negative time constant times natural log of I over I naught. So I is I naught divided by 2 divided by I. So time constant is charge times the resistance that the capacitor discharges through, and that's just R1. So that's negative R1 times C1, natural log of 1/2. So that is negative R1 10 kilo ohms times 10 microfarads, natural log of 1/2, and we end up with T equals 0.0693 seconds. So that is how long it takes for the current to fall to half its original value through this resistor.